Hey guys, welcome to the last video for chapter 7. Well, not the last one, but the one on radioactivity. So, last time we left off looking at alpha and beta decay, and we also looked at the questions for that. Um, so, gamma decay is the last one we need to look at. It's also the one that releases the lowest amount of energy in comparison to beta and alpha decay. Now, beta decay is actually the releasing of a photon, and it's symbolized by the gamma symbol, which is it's this little guy right here. This guy right here is the gamma symbol. So there are actually no changes to the structure of the atom itself. So the atom actually stays the same. It doesn't change to a different element like it did with beta and alpha decay. And that's because the gamma radiation is a photon that is being released. And a photon actually has no charge, as you see down here. But what is going on is this is kind of similar to things we looked at last lesson, where things were changing from a more excited state and getting closer to the ground state. So that's very similar to what gamma decay is doing, is that it's helping the atom itself become more stable by releasing just a tiny little bit of energy. Tiny, I say, in comparison to alpha decay or beta decay. Um, so in terms of this is sort of what a diagram looks like, which is fairly straightforward, just a release of a little bit of energy. Um, and if you were to sort of comparing alpha, beta, and gamma decay, um, alpha decay has the most penetrating power, and gamma decay sort of has the least penetrating power. We'll look at the diagrams for that very shortly. But what you're actually seeing here is that we'll talk more about this in half-life, but a little preview into that is a particle might undergo alpha decay, then it might beta decay, then it might gamma decay, it might switch back to alpha decay. So it can actually kind of swap back and forth between these three ways of decaying to make itself more stable. So here you can actually start to get a sense of these are the figures and tables to look at in Cognity. So if you don't want to look at it in this video, these are available for your reference in Cognity. So this is figure 5, which looks at, it's a more detailed version of the curve that I had sketched at the beginning of the last video. This one, though, shows that as we get into heavier elements, so there's a pretty steady upward trend away from, we're getting more and more neutrons for every proton. And it's not hard to imagine why we might need a few more neutrons, um, mainly because with more protons, there is a greater repelling force. And so we need sort of more things to keep the protons separated, okay, because of the electromagnetic repulsion force. Now, this isn't the only reason, but this is a very good reason to understand why we need more neutrons. And neutrons and protons have this extra little bit that we'll learn a little bit more about if you're sort of want to understand why. There are something called gluons that we talked about this last time that give the strong nuclear force. Okay, so more neutrons are necessary, but we don't want too many of them. More glue isn't always the best. So there is only so much works, and then for anything extra, you can see that if we have too many neutrons, it tends to undergo beta minus decay. And on the other side, we have beta plus decay. So a beta plus decay, we didn't get to really talk about this, is it's actually the release of what's called a positron. So a positron is something that is actually the size of an electron, but it has the charge of a proton. So that's what's called a positron. And it also has a matching neutrino, which is the electron neutrino, as opposed to the electron antineutrino that was created. So electron neutrino as opposed to the anti-neutrino with the electron pair. Anyways, we will cover a little bit more about that, but that's what this graph is referring to. So it can release positive or negative charges. If it's lower in terms of mass, if there's less neutrons, it tends to release beta plus, and if there's too many, then it tends to release beta minus. Okay, and you can see this is actually there's a little bit of an anomaly here, but generally speaking, when the elements reach sort of in the I guess probably anything above 50. So we're talking about anything in around the 60-ish area. It's starting to release alpha particles. So alpha particles um, is a fairly major change in the atom itself because it's giving off two positive charges and two neutrons as well. So it's a fairly major change. So that doesn't tend to happen unless the element is highly unstable. So I would probably characterize that as highly unstable. And during that time, it needs to do a lot more, which is an alpha particle. It needs to release a lot more in order to make itself more stable. And you can actually also see that there's fission happening, which is the splitting of the atom. So it can actually even split itself through the process of fission as well with the really unstable elements. Okay, so it's not just releasing the alpha particle; it's completely splitting itself into two vastly different elements rather than the release of an alpha particle. Okay, here we have a diagram for radioactive decay series for uranium. So uranium-238 tends to decay under this pattern. So it will first it'll give off an alpha particle, then it's going to shoot off two beta particles, and we're just sort of ignoring the electron antineutrino there, but we're focused more on the charge that is being given off because the electron antineutrino, if you remember, has no charge. So we tend to ignore this guy, at least in this current discussion. And then it continues to release more alpha particles and keeps releasing alpha particles until PO. I think, is that plutonium? Um, and then here it has a few different paths. It can release an alpha particle, or it can release a beta particle, then an alpha particle. So it can do it in two different orders, but it comes back to this element Bi here. And again, there's a few more different paths, but again, sort of an alpha and a beta, or beta followed by an alpha. So the order doesn't really matter, but it'll just produce a different element along the way until it reaches PB, that particular element there, okay? So here we're starting to see multi-trajectories. So whenever you see this happening, right, these are our betas, and then these are our alphas. So two different orders it could potentially take, but still reaching the same element, generally speaking, okay? So this is, there's a different chart like this for different heavier elements. And this is sort of what it might look like. So you may or may not be asked to ask questions of like, okay, so they might ask you, how many different paths could it have? How many alpha decays would it go through from, say, this particular point to this particular point right there? Okay. Lastly, we have a table that nicely compares and organizes all of the information. I'll give a short commentary here, which is, so first off, in terms of alpha decay, this is just the nucleus of the helium. So there are no electrons, and that is why it is purely a +2. As I mentioned a little bit earlier, is that the nucleus of the helium can actually rob and take electrons from other particles. With a beta minus, again, we're focused mostly on the negative charge. Excuse me. We're mostly focused on the negative charge, and we don't really care too much about the neutrino at this particular point in time. Gamma decay, there is no charge. So in terms of its ability to ionize, it kind of follows the charge. Okay, so +2, strong ionization. Even if it was a +1, if it was the antineutrino, so even if this was a beta plus, it is still moderate because it's only one charge as opposed to two. And the gamma radiation, consider that weak. Now, this is looking at, the other thing to also keep in mind is when we talk about giving an alpha particle and that the range of the alpha particle is only a few centimeters, this is a little bit different. This is looking at decay, which is the natural process of an element or of a heavy element breaking down, as opposed to something like a nuclear explosion, which might drastically change some of these different values that we see in this table. So this is for naturally occurring process of an element becoming more stable. So gamma radiation can actually be highly penetrating because it actually travels so far, and you need a lot, quite a heavy material in order to stop gamma radiation. Whereas with alpha particles, to stop helium, you just need, sort of like a piece of paper to stop that. Okay, but again, this changes under a nuclear explosion. So helium atoms could potentially be flying or penetrate a little bit, quite a bit more than what we're seeing here. Okay. But anyways, even if the alpha radiation did not destroy you, the beta and the gamma radiation probably would, unless you are underneath a thick piece of lead. And not only that, it would still also, it could also come around and like winds could also blow it back into, so even if you hit behind a piece of lead, particles can come back into you. So really you need full 3D shielding. Okay, that's getting a little bit off topic now. And in terms of radiation spectrum, continuous and discrete spectrum. So quick little connection back with our continuous spectrum, which is a full spectrum of light, and our discrete spectrum, which is a little bit more similar to the emission spectrum there. Okay, so that is roughly it. I encourage you guys to have a look and study this and look for patterns yourself. But that's the end of my commentary for this. See you guys in the next set of videos to finish off with half-life. Bye-bye.